All right, I think we can go ahead and get started. Um, Once again, welcome and thanks for joining today's US MAP webinar. My name is Jackie Petrie on the NREL Communications team, and I'm going to be running today's Zoom session. If you have any technical difficulties, feel free to send me a chat in the chat box at the bottom of your screen. You can also submit questions throughout today's presentation. We'll do a Q&A session at the end. You can do that by navigating to the Q&A box at the bottom of your screen. We'll try to check both Q&A and chat for questions, but if you could try to put your questions in the Q&A little box at the bottom, that way we won't miss any, that would be great. Just want to also let everyone know that we are recording today, and a recording will be made available later. So with that, I am going to hand things over to Yao.
Good morning, everybody. It's my pleasure to introduce Sam Rees, who's going to give the next seminar in the US MAP seminar series. Sam has a long history in working in analysis for clean energy and has a very interesting viewpoint that we wanted to make sure that folks working in the perovskite area are aware about, and how to think about the carbon impact of green technologies. Sam has a background in engineering and applied science. She got a degree from Yale University and has worked for many years in bringing products to market in industry. And so she has a really interesting sort of connection to the technology here. With that, Sam, I think you're ready to go.
Thanks, Yao. Yeah, thanks for the introduction. Before I came to NREL about 7 years ago, I primarily was working in volume manufacturing in Southeast Asia. And then I got an opportunity to come to NREL and kind of bring that experience. Also here today with me is the other co-conspirators on this work. I have Hope Wyckoff, who is a Chem E, graduated from Colorado School of Mines and has been doing research now for, almost 3 or 4 years, and has been here at NREL for approaching a year and a half. I also have Matthew Rees, who is approaching 2 decades in working on solar PV technology and is currently leading NREL's CAD-TEL efforts, although my understanding is he dabbles in perovskites too. And so just to kind of reiterate, we really want to make this interactive presentation. I know sometimes it can be really frustrating to have a question early on and not be able to understand until the very end. So please put your questions in the Q&A. Both Matt and Hope and myself will be monitoring them, and so we can take a pause anywhere along the way to answer. In addition, I don't look for this presentation to take the full hour. I look for us to have a lot of Q&A time at the end. All right, to kind of kick this off, how do we reduce the carbon impact of a green technology? And of course, as soon as I tell it, I want it. There we go. To kind of reiterate a little bit what Yao said, my primary focus here at NREL is actually doing work for the Advanced Manufacturing Office. And so we were approaching this project from a slightly different lens than necessarily would be done if we were, for instance, doing work funded by CETO. The Advanced Manufacturing Office to be focused on the nation's critical material supply. And so I had been asked to investigate the energy and carbon impacts of critical materials and recycling on energy technologies, and try to understand, in addition to the embodied energy and the embodied carbon, what is the feasibility of having a circular economy for just getting those critical materials so we don't have to have as much dependence on other sources. Now, this meant that we basically had tellurium as the PV material that was identified as the critical material with direct relevance to U.S. manufacturing. And so when I was first given this project, I was a little bit at a loss of what to do, because I was just given these were our goals, and I was like, I don't know what to do with this. And so it turned out that we had a long drive up I-70. For any of you who live here in Colorado or visited Colorado and tried to go up I-70 during ski time, it gives you a lot of time to think. And so we were bantering back and forth, you know, what could we do with this? What would make sense? Because the other thing, especially coming from industry, I really want the work we're doing to have relevance and be able to be utilized by the community afterwards. And so that's kind of the basis of where we got started and the lens we were doing this in. And as we like to say, you know, this makes a really good marriage between analysis and science. All right, I already kind of was throwing out some different vocabulary, and I have to confess, most of my work is focused on embodied energy, embodied carbon. So I was like, of course everybody knows what this is. Turns out, for those of you who do not live and breathe this is not necessarily intuitive. So embodied energy is the energy consumed to mine or harvest all the way back from raw materials to a finished product. This includes things like transportation. Same with embodied carbon. Embodied carbon is the CO2 released from starting all the way back at the mining of the raw materials through the transportation of a finished product. Now, when you're talking about these things, you are often talking about analysis called LCA, life cycle analysis. And you will either do that from cradle to gate. Cradle to gate is from mining extraction to the end of the manufacturing of that product. The other way the analysis is often done is cradle to grave. Going cradle to grave means you start at the mining or the extraction and you go all the way till the end of the life of the product, and that product has been disposed of, recycled, or found a second use. For what we're going to do, it's going to be cradle to gate, but that kind of just sets the parameters of how we're looking at this. Continue kind of giving a little bit more background. So the tool that we're going to use to do this life cycle analysis for our project is called Materials Flow Through Industry Tool. This is a tool that the Advanced Manufacturing Office has been funding for over a decade. And it is based, if you're just doing the defaults, on the U.S. Energy Grid averages. And you essentially put a recipe for whatever you're wanting to manufacture into it, and it can then generate what is the embodied energy or embodied carbon to manufacture for that recipe. And it has a big database behind it. And that is that is the tool we are using for our calculations. Then, just to kind of iterate for this group, it is a free tool that you can use. The current administration focus, and a lot of the new funding opportunities coming out are starting to talk a lot more about decarbonization, embodied energy, and whatnot. So this is actually a tool. You can Google MFI NREL. It'll take you to the website. You can sign up. And this is a tool you can use for your own projects if you want to be able to get an idea of what these are. All right. So going a little bit more to what was the project, we decided to use as our model cases silicon PV and CdTe PV. And so we consulted with different experts to kind of get an idea of what are the current state of the art. We thought that CdTe makes a really good approximation for almost all thin film PV, as it's a super straight technology grown on glass with a TCO. So since, today we're talking to people who are interested in perovskites, while obviously there are differences between CdTe and perovskite, from the purposes of this analysis, there should be a pretty close approximation of what the embodied energy and embodied carbon initially at least would look like. All right, so how did we get going on this? So our first step was to basically do a fairly comprehensive literature search, pulling values that other people had done, because it's not like we reinvented a wheel and nobody had done a life cycle analysis before. And so we wanted to make sure that whatever we were doing was in line with what had been previously reported. So we, for both CdTe and silicon, pulled the literature values. And then what we went and did is we went and got the latest recipe. For CdTe, it was the latest design from First Solar for their Series 6 module. And then for the silicon, we got a bifacial recipe from a Key State lab, and that we in analyzing it, think it's a close approximation to the state-of-art LONGi module. So once we have that, we put it into MFI. And when I say we, I actually mean Hope. Hope did all the LCA analysis for all of this. And so this is the royal we. And then we looked at what is our values compared to what we were seeing in literature, and that's what you're seeing here. And again, I'm going to highlight we were doing cradle to gate, so we only looked through the finished manufactured product. And you can see, obviously, our values are a little bit lower than some of what was in the literature, but we are also at least 3 years newer, so we're using more state-of-the-art, and a lot of things have changed. There's been a lot of material reductions and other things. So we felt fairly confident that we were starting at a baseline where there was nothing crazy that we were doing. We were confident in our tool, confident in our recipes. And so starting from that standpoint, we ran the numbers. All right, so energy payback times. It turns out one of the things we found when we were looking through literature, energy payback time is a favorite way of comparing technologies. And so we wanted to kind of figure out the energy payback for a CadTel module versus a silicon module. Now, I want to take a moment and caveat this. We understand energy payback times are more typically for a system. And so in our case, though, what we did is we just modified, and we are looking, this is the energy payback time to manufacture that module. But we do understand typically this is more of a system sort of equation. But if you read through a lot of different papers, a lot of people report on an energy payback time of modules alone. So what we found is that you basically, energy payback time of a CadTel module is about 2.5 months. What does this mean? That means that you make this module, you get it out in the field, and after the first 2.5 months, it is basically just generating the energy that had been necessary and consumed in order to manufacture it. That means for the next 29 years, 8 months, and 15 days, all the energy it generates is excessive of what it had taken to manufacture it. A silicon module took closer to about 6 1/3 months to have an energy payback. One of the things that we were surprised to see is the semiconductor for a CadTel module is only about 1/3% of the embodied energy, whereas if you look over here at the silicon, it is closer to 5 months. And I'm actually going to turn it over here to Matt to kind of talk a little bit more about some of the other technical things we came across here.
Yeah, so just to understand why the semiconductor for silicon would contribute so much of that energy payback time relative to CadTel can be understood in a few different ways. One of them is that the thickness of a silicon wafer is typically, a couple hundred microns compared to 3 microns for CadTel. So you've got, say, a 50 plus X difference right there. But then there's also difference in the purity requirements for silicon, and that's also can be understood through this lens of thickness. So as you make something much thicker, if you are going to have an impurity, like the same type of effect of impurities, if you do a random walk and your random walk is now 50x longer and you cube that, that means that your purity to have the same level of impact of these defects has to be 50 cubed. So those two things actually contribute an enormous amount to the energy required for the purification of silicon. And then there's also just an enormous amount of energy to strip oxygen from silicon sand. So those are really kind of the driving factors. But so one of the reasons why this is a good proxy for perovskites is that you can see that all of these aspects that are really driving the energy for CadTel are going to be really similar for a perovskite, your glass and your aluminum frame. And we actually were trying to be pretty conservative with our energy consumption numbers. One of the reviewers actually came back and said that we were overly conservative, but we were trying to use internal models, rather than something else. And we were already coming down pretty hard on silicon. So, yeah.
Yeah, so it is definitely, as Matt noted, in a thin film module, a third of your energy is the glass and a third of your energy is in the frame. So from a perspective of potentially decarbonizing a thin film, you know, there is a lot of other areas that are going to be just as impactful as, you know, tackling the module manufacturing itself. All right, so kind of going back though to, you know, what the project's original mandate was, is we wanted to then look at going ahead and recycling. Now, first, I know there is a lot of excitement about recycling PV modules out there, and I share it, and I think this will be great. But I want to bring to focus that these are 30-year products. We are not going to have a substantive amount of material to recycle until probably about 2046. This graphic I'm showing here is from a recently released paper where they were using an NREL tool called PV ICE to kind of estimate out what is deployment, what is going to be available from the recycling perspective. So recycling is going to become critically important, but we're not actually going to have a ton of material until quite a few years from now. Nevertheless, the question actually came down to, you know, is it reasonable to recycle CadTel modules in order to recover the cadmium and the tellurium as a critical material and reuse it into another module? And using the same methodology I described, we were able to ascertain that if the only thing you recovered from a recycled module was that cadmium tellurium, you would only have a minimal bump in the amount of energy it took to manufacture that module. Now, however, if you're going ahead and you've already collected the module to recycle it, it's super trivial for you to go ahead and strip that aluminum frame and recycle the aluminum. And so if, in addition to cadmium and the tellurium, you go ahead and recycle that aluminum frame, well, then you actually now are going to use considerably less energy than it took to make it out of all primary materials. And in a futuristic world, and by 2046, we should be there, if you could go ahead and recycle the cadmium, the frame, I'm sorry, the CadTel, the frame, and we had discovered a methodology in order to do like-to-like glass manufacturing, because currently you can recover the glass from a module. However, that glass is not recycled back to PV glass. It is downcycled into container or other types of glass. And from the purpose of LCAs, that technically doesn't actually count as reducing your embodied energy and body carbon. But again, in a futuristic world where you can do that, you are almost half the necessary energy than if you were using primary materials. So going back to that energy payback, and now we kind of had been able to use a few, get a couple other ideas of what the amount of energy to manufacture a CadTel module would be. Same with silicon. The energy to recover a silicon the aluminum frame of a silicon module or the glass of silicon is going to be the same. We kind of then wanted to look at the energy payback of what will this do, you know, as you are able to use more and more recycled materials. Something we learned, and it was kind of eye-opening to us, is that your grid in the way that energy payback is defined to be calculated, you actually put in a grid efficiency, which is the primary energy to electricity conversion on the demand side. And so this actually counterintuitively means that as the grid starts to go to a higher renewable penetration, the energy payback calculation will actually mean that it'll take longer for these renewable technologies to pay back. And so currently we're in the upper left-hand corner with CadTel, and as we come down to using all recycled material, but then the grid efficiency goes closer to its more renewables, you know, the energy payback time will be somewhere between, you know, about a month to upwards of 5 months if we had a 100% efficient grid, which was never going to be possible, but we will get closer. Matt, anything on energy payback you want to tackle here?
I guess the reason we ended up not doing silicon was just that there was no proposed silicon recycling process that was
viable.
That was, really well accepted.
Yeah, so this is not to say you cannot and should not recycle a silicon module. You obviously can easily strip that aluminum framing off, and that aluminum, recycled aluminum, has a significant smaller carbon and energy footprint, and same with the glass. But we were not and did not try to tackle what it would look like to recover those wafers, because there is no process that, when we looked into being able to do the analytics on it, made sense, and it's just not yet there. So, all right. So the next piece that we wanted to do is in order to figure out, we want to kind of expand this to be more global. As I said, the default in the MFI tool is to use US grid mixes, but obviously PV is manufactured across the world. And so using silicon and CdTe as model cases, we wanted to kind of get an idea, where is this value chain? Now, my guess is most of you have seen this map or similar. For silicon, you can see the vast majority of the value chain is sitting in China. However, one of the things that we didn't have available and hadn't seen one of was a map of CdTe. And so, yes, silicon PV modules are the dominant deployed technology in the world. Over 90% of the modules in the world are silicon. However, in the United States, CdTe is 40% of the US axis-based tracking market, and 25% of the cumulative installations greater than 1 megawatt. So this also reinforced that, looking at CdTe as one of the technologies was really important. And as you can see here, CdTe is manufactured in the United States, in Vietnam, Malaysia, and India. Also, you have a little bit going on there in Europe. And so this kind of led us to want to look at a variety of grid mixes. So we thought, obviously the United States, obviously China. Those are the two dominant ones. And then we thought we would also look at India and the European Union. As an added bonus, this array of grid mixes is also a good representation of possible energy out there. If you look, you have India and China that in the 2020 grid, so their current grids, have a lot of coal penetration. In the United States, you have a lot of natural gas. And in the EU, you already have quite a bit of renewable penetration. So for a lot of different people who are wanting to understand what is the impact as the grid changes and goes more to renewables, these also are great mixes to be using, because they can take these values, be less specific about them, and just use them instead of representative of what happens as you move from coal to renewable. All right, so using these grid mixes, then we went ahead and ran the same analysis that we showed before, looking at, though, the manufacture of these technologies at each of these locations. And when we were looking at them, so manufacturing CdTe in Europe, US, China, India, same with silicon. And as you can kind of see, that the difference between CdTe and silicon is about 2x lower when you have the same mix, and that the mix then can change each of those amounts by about another factor of 2x. Okay. All right, so I kind of started off our talk today talking about all this embodied carbon. I'm sure all of you have been hearing about embodied carbon, but why do we care? And this is also another thing, as we were bantering back and forth, Hope came to us with the results and is like, look, it takes this much carbon to make a CdTe module. And all right, well, great. But now, what does that mean? What is this amount of carbon? Okay. And so, where do these carbons come from? And it's based on the carbon budget. And with COP26 having been recently, the Paris Accords, the goal is to limit a temperature rise to 2 degrees C. Ideally, in a happy world, we'd keep it to 1.5 degrees C. And so the IPCC has a carbon budget of which they have confidence levels of which this will actually happen. So the IPCC has calculated that with a 50% confidence that if, starting at the beginning of 2020, we only generated another 500 gigatons of embodied carbon, we would be able to limit the temperature rise to only 1.5 C. And so what we want to do is then take what these values where we calculate for each of these panels and put it in kind of a, okay, what does this mean sort of analysis. And that's what we've kind of done here. So what does it mean to manufacture 1 terawatt of the PV technology on these different grids. And so what you can see here is manufacturing a terawatt of silicon on India's grid in 2020 would result in you generating 0.1% of the 2 C IPCC 50% confidence budget. However, when you go to what their 2050 grid would be, then you are going to instead be at the 0.1% of the 1.5 degree IPCC budget. Also, kind of, again, going to the, what does this all mean? Because as we were staring at these numbers, we're like, okay, what is that in relation to? And so if you look at the very top of this graphic, the green line is the emissions from the 2019 US electricity generation. So the good news is a terawatt of PV manufactured on any grid is still less emissions than what we had in 2019 to generate our electricity. However, as you see in the EU, in 2050, manufacturing either a terawatt of silicon or a terawatt of CadTel is putting you under the 0.1%. So the other thing to take away, and again, I will iterate, I work mostly for the Advanced Manufacturing Office, where we really focus on manufacturing and U.S. manufacturing. Manufacturing CadTel in the U.S. versus China manufacturing silicon mitigates over 786 megatons of CO2. So there is a significant difference both with technology and geographical location where you choose to do it. All right, what is the implications of this? All right, so one of the questions we've been always asked is when we're graphing this, why did we choose a terawatt? Because it's easy. You can multiply a terawatt however you want and get whatever values you want. So we chose a terawatt for that reason. So what we did is we pulled out a couple more papers to get estimates of deployment of PV by 2050. And of course, it varies anywhere from about 77 to 70 terawatts. And so then to put things in context to meet these 2050 deployment goals is if you assume all silicon PV is produced on the 2020 China grid, so you assume you hit that 7 or 70 terawatts silicon only on a 2020 China grid, you are going to consume between 2 to 17.5% of the entire IPCC's 1.5 degree 50% budget. Now, I want to note, this is for modules only. We are not including anything such as racking, inverters, or other builds, balance of system things. If you assume that you deploy 100% CadTel produced on a 2020 US grid, you will consume between 0.6 to 6.3% of the IPCC's budget. Now, we are not saying we should stop producing silicon. Absolutely not. Any PV is going to, like you saw the green line, like the electric emissions from the US in 2019 is way above a terawatt of PV, no matter where you produced it and what your technology was. It is just to kind of give a relevance of where we should focus on trying to decarbonize this already green technology. And again, to kind of reiterate for this audience, we think emerging thin film PV perovskites would be on par with the CadTel. Again, going with the more advanced manufacturing focus, if you put this in context, if you actually assume that we're going to get to about 57 terawatts of PV in 2050, and you do out your math, that's about 2 terawatts a year, that would mean that producing PV silicon modules would become the #1 industrial emitter, eclipsing even metals, chemicals, cement, and so, that really kind of drives that there are opportunities here for decarbonizing this industry. All right, I'm going to toss this over to Matt to talk about let's decarbonize.
Sure. So basically, we kind of established the bounds there for the different grids, and all of those numbers we're really just looking at 2020 because that's current. We weren't including balance of systems and things like that. And you could kind of say that it's maybe a little bit alarmist because we know things are going to get better. But it gives you still an order of magnitude, and maybe you end up dividing those numbers by 2 or so when you go and you look at the two ends. Once you go to a grid value But for ways that we can actually, say, make a thin film even better, because it's already way better than silicon. So just choosing a thin film technology gives you about a 2x reduction on a individual, same grid mix. But going and, moving to a different grid, that can improve things. We've kind of, seen those levels of changes. Now, efficiency improvements is also another area, and you can kind of understand what that level of efficiency improvement might be. For cadmium telluride, it's the module that was modeled was about a 19% efficient module. So the community is trying to improve the efficiency, and certainly perovskites are aiming to be able to hit high efficiencies. So if you were able to improve the efficiency over a 19% efficient module, then there's the opportunity for maybe a 25 to, say, 40% reduction. So bifaciality is another thing that has been considered in trying to improve energy yield. And really the reports vary widely on how effective that is. Some have been as optimistic as saying 25%, others are as low as a couple percent. So you can kind of view all of those as giving you a ballpark thing. But the biggest factor you can really do is the technology choice, and the next biggest is your grid mix. One other thing that Hope had noticed, and maybe she could go and comment on, was that we don't actually bottom out our, like when we go to these grid mixes that are very efficient, we don't actually bottom out our emissions. So do you want to field why?
Sure. So a lot of this can come from the manufacture of different materials. Our emissions can come from a few different places. One of those is certainly the emissions that come from the electricity we use, which as we go to a renewable grid, those emissions will be eliminated, but other emissions come from the actual chemical reactions it takes to achieve certain materials. A good example is glass. And one of the precursors to glass making is limestone, which has a carbonate attached to it that is released once it's heated in a furnace. And so these CO2 emissions will not be eliminated by achieving a renewable grid and will have to be addressed some other way.
Okay, so we just noticed that there are questions, but somehow they weren't showing up for Matt and Hope, and we apologize. So some of these questions are going to go back ways. One of the questions is, how do you determine where exactly the gate is? So when you're doing cradle to gate, it is the end of manufacturing the product. So at the point that it leaves the manufacturing facility, that is the end of gate. So it's cradle to gate or cradle to grave is the common definitions. So also within the semiconductor portion of the energy payback time plots, how much is from the absorber versus from the transport layers or buffer layers?
Did a sensitivity analysis. So we did a sensitivity analysis for the semiconductor and the thin film, and when Hope did the sensitivity analysis of the non-CAD-TEL portions, she found that they were almost negligible, if I'm remembering correctly. The zinc TEL layers and the various other portions, right, Hope?
Yes. Why recycle a module if it's still producing 80% of the initial power? So, excellent question. It is more of a policy thought. A reason why you may repower a field is if the value of the land is such that the additional energy justifies it, this is beyond science, right? Obviously, if it's producing 80, you're still getting energy. The more energy you get out of it, the less you actually had to manufacture. On the other hand, land and space and infrastructure cost money. And so if you've reduced 20% your initial power, and so therefore you're having to put in more, then you can then need to have an additional cost associated with the infrastructure to support those. That's more on a policy and a TEA sort of perspective. But I mean, yes, obviously, you know, you could make an argument that you should keep using them for longer. Do I think Ian might be a good test of how PV modules will hold up under severe weather conditions? Yeah, I think we've already had a few hurricanes that kind of tested PV. I believe that there are some really horrifying pictures from the last hurricane from Puerto Rico, of not the 2022 ones. You know, when you have 150 mile per hour winds, my understanding is it kind of rips apart everything.
Although I did, there's an interesting, I don't recall the company now, but I can look it up if people are truly interested. There's a proposal that a company made to actually install PV instead of in a racking system that's off the ground, but to instead install it directly on the ground with no spacing between them. And though that system is supposed to be able to withstand hurricane level winds. There's some clearly other things that you know, need to be considered because the temperature is going to be different. But you can pack your modules together a lot more closely, so land use is actually pretty good. So it's just different trade-offs that get made. So there are configurations that wouldn't require necessarily changing a module design, but it may be a racking configuration that you do.
What is likely to be the environmental impact, and how do you recycle the damaged panels? I can't talk about that right off the bat of how you do it, because it all depends on your degree of damage. I mean, obviously, if you shatter into a million pieces, it makes it much less easy to gather them up and get them back to the facility. I mean, you can still recover the CAD and TEL form. You can still get the aluminum. So, I mean, it can be done, but from a TEA, a techno-economic perspective, obviously, this becomes a lot more complicated handling and adds a lot of cost and other things.
My understanding on module design is that thin films are more robust typically to a lot of impact damage, where as long as you don't break the glass, you don't shatter the cells, where with wafer-based technologies, there's a lot more concern about getting fractures in your wafers, where even if they continue producing power immediately after the fractures, that there may be long-term loss as a result of that.
Does our analysis include premature end of life due to climate change events? Well, so technically that doesn't actually impact anything, as long as you basically get the 2.5 months for CAD/TEL or the 6 months for silicon. Like it doesn't really impact what our analysis was, the fact that these panels may not make it to their 30 years, because we are only going cradle to gate. We do not include, you know, some of the effects and the energy and embodied carbon that may be happening as extraction, you know, might be impacted by climate events. That's it, just for the purpose of our project was kind of outside the scope. Did we do a carbon per terawatt calculation assuming a continuous change in the grid over time, or just using the end cases? We just did the end cases because we actually started doing it over time, and then my head exploded. And so we were like, if we do, what we did, this is why when we did this, we also didn't do, like, currently there's a 90-10 distribution of silicon versus thin film. We didn't do any of that, because then the explanation of what the boundaries are becomes so long and arduous that it becomes very hard to, like, noodle through. We did very simple, 100% CAD/TEL, 100% silicon, 100% on this type of grid. And then that way we wanted to enable the community to be able to do with that as they will, because, you know, it is all encompassing. And then you can you could take, hey, what if I had 50% CAD/TEL, 50% silicon, or whatnot? What would happen in terms of carbon emissions if perovskites looked exactly like CAD/TEL but had a significantly shorter module lifetimes? Nothing. And again, as long as you pay back, you know, if you look at energy payback in 2.5 months, you pay back a CAD/TEL. So if you, for the purpose of emission, we are looking at how much does it take in order to generate. So it's not going that, it's not going to change much in the way we were doing these calculations. Now, for then when you start to look at so if a perovskite only had 5 to 10 years, then obviously as we're doing this deployment, you're going to have to start adding back in the perovskites earlier than we would have here. And so I guess it would change how much of the carbon budget it might eat up, but then it also depends on other pieces. So it's a complicated question that would require really setting up the equations clearly. And I think I have now gotten through, and again, I apologize, they were looking, there's a difference, I guess, between presenter and what they're able to see. So I'll try to make sure. All right, so we already talked about the knobs. All right, takeaways. A little bit, this already ties into what Matt talked. Manufacturing location technology choice can mean a 3x difference in carbon. So for different researchers and other things, you know, what does this mean to be? Well, maybe we should be thinking about decarbonizing the frame. What if you did something like a new material and did densified wood? This is sure just merely, you know, a thought, but, you know, there's this natural wood out there that you can see in the graph is just as strong as the aluminum alloy.
Also, after we did this analysis on a Series 6 module, First Solar recently announced a Series 7. And in the Series 7, they have reduced the amount of aluminum so that they've gone back to a frameless module, and they just have 2 aluminum supports down the center for the frame, or for the mounting to the rack. So they are going and reducing the embodied energy further. That I don't know exactly what they've done to change the thickness of the glass. There's clearly a trade-off there. And they've also been looking into things like having different thicknesses of glass on the edges of their utility installations versus in the center, where you have different wind loading events. So there are a variety of other types of things that you can do to try dialing those knobs.
And again, iterating on the glass, you know, that's an important piece for thin film. In the case of CAD-TEL, that's 52% of your emissions. Obviously, with silicon, it's a lot less. It's only 18% because in silicon, the semiconductor is a significant contributor. There are some talk with silicon of some different ways of doing some wafering and having reducing your kerf loss, which would just improve that in the silicon world. The other thing, just kind of tossing out there, is that carbon tax could mean you could pay between 2 to 4 cent difference watts for silicon versus CAD-TEL manufactured in the U.S. So, you know, you could justify some of the higher costs for choosing a different manufacturing location if you were talking about something like a carbon tax. Anyway, thank you. We had a lot of different help on this. You know, we had help with the MFI tool from Scott Nicholson and Shub. We also had a lot of different discussions with different people, Brady Carpenter, Nancy Hagel, Mark Ruth, Joe Barry. Joe Cresco is our program manager at AMO, who is awesome. If you guys want to chime in with some questions here, happy to answer some, you know. Oh, I guess I can turn on my camera if I could.
Awesome, thanks, Sam. Did you see Emily's questions in the chat? I think there were. That's in a different location again, so it's a.
Yeah, we caught Emily's.
Okay.
She had some carbon questions, and
Yeah.
I think I caught some of the questions in the QA. Anybody else have any questions? And of course, if you don't like to talk in a group forum, totally understand that. You are welcome to reach out to any of us, and we're always happy to talk about it. You can also just go read the paper. There, a lot of our assumptions. We also did a really comprehensive supplement, so you know you can see where our boundaries were, what materials we were assuming, and everything there.
So I do have a question about. I mean, you did talk about the comparison between CAD-TEL and perovskites, and that there really is that the Cattell case would be is very close to what you expect for a perovskite case.
Yeah.
What kind of things? I mean, what could you imagine would significantly change that picture? I mean, people in the perovskite space talk about solution processing being a major factor, maybe, and that sort of thing. And your analysis, this might come into the manufacturing intensity piece and not in the materials piece, maybe.
Right. And so the manufacturing intensity piece for CAD/CAM was about 30%. So
Right.
if you're solution processing, you know, you'd be able to kind of chip away at that like 30% contribution. So that would be that piece. The other thing, you know, both CAD/CAM but perovskites, if you could put it on a different substrate, you
Right.
know, I know there's really a huge focus on making them flexible and whatnot, and then I mean, clearly the glass is about 30%. And, you know, Matt talked about there's other things out there to even thin out the glass. But if you're solution processing, recycling the solvents could seriously impact your environmental footprint. Also going to lower temperatures. Sorry, this just decided to stop sharing. But let me show. Because Hope and I have our current favorite other solution for things is, why is technology, you'd think by now this far into things our technology would not
Yeah.
and yet it just stopped sharing. Anyway, our if Hope and I's like big thought is, you know, the US, if we're going to grow, especially since we have such a dominant position on CAD/CAM manufacturing, we're going to need to create at least another 2 float lines for our deployment. And so what if you actually co-locate the glass manufacturing with your panel manufacturing? Therefore, instead of having to heat up the glass when you're manufacturing it and then you cool it down and heat it back up again, you just keep on going and you reduce your energy there. So, you know, these would all have opportunities for reducing.
Yeah, but still a lot of your energy is going to still come from just how do you make that module package?
Mm-hmm.
So, you know, the lamination and whatnot.
Yeah.
But potentially if you could go to, you know, move away from glass with a low energy flexible product that has a barrier, that may be an opportunity for perovskites.
Yeah, the barrier, yeah, you still need those very good barrier properties indeed that the glass has, but yeah, in different materials. Very cool. Well, this was a wonderful talk, and thank you so much, Sam and Matt and Hope. I think that's a great contribution from the team, and yeah, contact the team directly if you want more info. I think I already fielded some questions about that and how to contact you all, so I'm sure you'll hear more. And okay.
Well, thanks for the opportunity to talk with you guys. And again, reiterating what y'all said, please, we're happy to answer any questions, and so feel free.
Wonderful. Well, thanks so much, Sam and folks. This was fantastic, and thanks everybody for attending. And I hope to see you at the next US MAP seminar.
Thanks.
Thank you.
Thanks.